the theorem. This is the famous Jacobi relation. Jacobi, three-diagonal relation. I will not prove in one dimension. We will give directly the proof in many dimensions. You will see that the proof essentially is the same also in infinite dimension. So the Jacobi relation means there exist two sequences, omega n and alpha n, such that omega n are positive and they have a very, very important property. And they have the property that if omega n is 0, then omega n plus k is 0 for all k. While alpha n is arbitrary real sequence, can be chosen arbitrarily, okay? So there exists the sequence of omega n, a sequence alpha n. Omega n satisfies this. Alpha n satisfies this. It belongs arbitrarily to real line, such that if I multiply, these are called to be, I call the phi orthogonal polynomial. We should be a little bit more precise. We call them monic. Monic phi orthogonal is useful in the notation. You can be confused because, for example, in physics they use so-called symmetric, the normalized orthogonal polynomial, and so this relation is that I'm going to write is slightly changed. It's called symmetric Jacobi relation. But we write this Jacobi relation as the original one, as you find in the standard books on orthogonal polynomial, is what I will write now. So if I multiply the nth orthogonal polynomial by x, I get the n plus 1 plus alpha n phi n plus omega n phi n minus 1, with the convention that phi minus 1 by definition is 0. Okay? This is the famous Jacobi relation. Now, you remember that I mentioned it in the beginning, I mentioned the quantum decomposition. The quantum decomposition is nothing but a reinterpretation of Jacobi relation. Nothing more than that. So, if you define the operator A dagger phi n equal by definition phi n plus 1, and you define A0 phi n equal by definition alpha n phi n, and you define A minus phi n equal by definition omega n phi n minus 1, with the same, I will always keep this condition, f phi minus 1 is 0. Then you have three operators, because phi n is an orthonormal basis. They are linearly independent. You see, here we use monic. They are linearly independent also algebraically, because when they are orthogonal, in Hilbert space implies linear independence. But in pre-Hilbert space, not. They can be 0 not. So, linear independence and orthogonality in pre-Hilbert space is not exactly the same thing. But in this case, they are monic polynomial. So, by the principle of identity of polynomial, they must be linear independent. A polynomial of higher degree cannot be linear combination of polynomial of lower degree. Okay? So, they are linear independent. So, I can always define operators A dagger, A0, and A minus using this definition. And then, by definition, I will have, since this is true for every n, then I will have this x equal A dagger plus A0 plus A minus. Okay. And you see, so you see the quantum decomposition is in some sense something that could have been discovered 150 years ago. But of course, 150 years ago, a lot of functional analysis where operator theory was not known and so on. But how do you see?
Yes, so this omega n takes values in positive fields?
Are truths, are plus. Omega n are always positive.
Positive.
Are plus. They are element of R plus. Alpha n are arbitrary. But they are positive. Omega n are positive. This will be very important. But this condition is more subtle. And you will see essentially this condition. Now we have a quantum interpretation of this condition, and it's exactly the condition that guarantees the possibility that the creator has an adjoint. And then we can define an equilibrium. Now we have now defined this, but let us see some corollary from this reinterpretation of Jacobi relation. We didn't put anything new, just reinterpret Jacobi relation with this. But now you see, A increases the degree. You see, the polynomial algebra, we have said, at the beginning I wrote the monomial gradation, which is a vector space gradation. But now with the phi n, we have the orthogonal gradation, which is a orthogonal gradation, and also a direct sum gradation for the comment that I said before. Okay. Now, in any graded Hilbert space, you can speak of degree of this is graded by the integer. So you see, this increased the degree by 1, and this decreased by 1. So it means that A minus A daga leaves the gradation invariant. In fact, you can compute explicitly in our case, because A daga will bring to phi n plus 1, and A minus to omega n phi n, but now omega n is omega plus 1. So this will give omega n plus 1 phi n. Similarly, you do A plus A minus. You apply to phi n, and you obtain, by definition of A minus, omega n A daga phi n minus 1, but A daga just adds a 1, and so you have omega n phi n. So if we subtract, we have that A minus A daga minus A daga A minus applied to phi n is equal to omega n plus 1 minus omega n phi n. But this is true for every n. So I want to write this as an operator equality. For this reason, I will introduce the number operator. I will define an operator which has this property by definition. Lambda n phi n equals n phi n for each n, and this I will call the number operator. Okay? I will call the number operator. Then I can write this in operator language. I will use this to define for an arbitrary function f. I will define the operator f lambda by an implicit use of spectral theorem. Fn times c. So what is f? F is a function defined on the spectrum of lambda, which is the integers, the natural integers, and it goes into, it takes a natural integer and it brings it to a complex number. So for any function, I can define the function of the operator. This is a kind of implicit spectral theorem. And then with this notation, the commutation relation becomes A minus commutator A plus, which is, this is the commutator, equal omega lambda plus 1 minus omega lambda. You see? And this is what you remember in my introduction. I introduced this partial omega lambda. So this is my definition of the symbol partial omega lambda. It's a difference operator. That is why I use the symbol of partial derivative. But it's a difference operator, not a differential operator, but difference. Okay. So you see that now what I was anticipating. You have commutation relation associated. We started from any random variable, because when we put a measure on the polynomial algebra, we have a random variable. Conversely, given any random variable x, I can do the polynomial algebra in x, and the measure gives me a state. So any random variable with all moments has its own commutation relations, which are uniquely determined. Well, you can do as an exercise to compute the commutation relation with A0. They are very useful because, you see, what happens? We compute the effect that we will do something more general. Not only we compute the commutation relation, of, for example, A plus with F lambda, any function of lambda. A0, what is A0 in this language? In this language, A0, we can simply write A0 is alpha of lambda. So remember the definition of a function of lambda, but A0 has been defined by this. So if you compare with the definition, A0 is nothing but alpha of lambda. It's clear? Okay, so now you see, if I apply to phi n again, F lambda is gradation preserved. So I will obtain, and A daga is linear. So I will obtain Fn A daga and apply to phi n. This will give me Fn Fn phi n plus 1. Okay? And what is this? This is let me write here. Do you see here? Can you see if I write here? Or no? You see? Okay, so this is equal to F lambda minus 1 A daga. See, because if I apply A daga to phi n, I get n plus 1, and if I apply F lambda minus 1 to n plus 1, I get lambda, which is phi n. Okay? So I have this very simple commutation. So I have much more than commutation relation. I have the multiplication table, because you see, we have much more. We have this explicit, we have this explicit, and now we have calculated this. And you can do for exercise or in fact, taking adjoint, you get the commutation relation for A minus. Okay? And using the fact that F is arbitrary.
So you were saying you were saying that you would compute the commutation of A0 with this A plus and A minus.
It's more than computation. This is just a multiplication table. It's even more than commutation.
For any function F.
For any function F. For any function F. A daga is specific, of course, because you cannot speak of function. You can only speak of polynomial functions. They are not self-adjoint. but they have eigenvectors both. So in some sense you could also speak, but this is not up to now. What I want to emphasize, and when we will discuss the notion of normal order, this will be very important. Of course, we have only, also in quantum mechanics we have. But I have seen, for example, when you define the normal order in physics, that there is the psychological prejudice to use only AA daga. But if you use AA daga and the preservation, the normal order becomes a much easier and more elegant formula. So you see, even in the standard quantum mechanics, this approach gives you a deeper insight. Okay, so now we have. You said that I should not.
5 minutes is okay.
5 minutes. Okay.
3:15 there is another problem.
No, 5 minutes we cannot do the Favart lemma. Favart lemma is more subtle. You need to argue a little bit. We can do less time. Yes. Okay. So this is a good moment to stop. Okay.
Any questions? Okay.
Yeah, good. Question.
Will you please explain that first line once again? That you wanted to see the manifold, right?
This one.
No, top line. Yeah, what do you really mean there actually? First line, you wanted to see just a manifold or something, you said. Yeah.
This line. I put coordinates. I say, usually we say that a one-dimensional vector space, real vector space, is equal to R, but it's not true. This is not true. It's only equal when you fix a basis. For example, in physics, this has an important physical meaning. To fix a basis in a one-dimensional space means that you are fixing the measure unit of your random variable. It can be length, it can be seconds if if R is interpreted as time. You see? So the basis is not a mathematical pattern tree. It's a very deep physical meaning. It means you are fixing a unit. In a manifold, there is no, the manifold is defining by local coordinates. So you never need the local coordinates. Okay?
So one thing. So you get the equation A plus F lambda is equal to F lambda minus 1 A plus.
Take the adjoint and you have the commutation with the table of multiplication with A minus.
Yeah, but what I'm saying is, so the commutation of commutator of A plus and F lambda.
Yeah.
That would be
You write down. Once you have the multiplication table, you have much more. Of course you have the commutator.
Yeah.
You see? Of course you have. But I want to insist that the fact that we think in terms of commutation relation is a prejudice that we inherited from quantum mechanics. But in fact, if you do the calculation, you have much more. Because the multiplication table is much more than the commutation. Once you have the multiplication, for example, you can do as exercise. You can now compute the anti-commutation relation. Because it's closed. Also the Jordan bracket. Not only the commutator, but anti-commutator. And you will see that you discover a very interesting feature. That this algebra is closed also under Jordan.